Good morning to each of you, and welcome to Science Symposium 2019. This is our second day, and I am absolutely delighted to start to announce that Nigel Nunn from Australia, so he's come halfway around the world to speak to you today, is going to give us a wonderful presentation. Nigel grew up in Sydney, Australia. He first read the Urantia book in 1980 at age 19. Deeply impressed by the descriptions of personality and automatons, and intrigued by the implications about interaction between things finite and absonite, Nigel decided that automatons were worth a deeper study. He completed his bachelor's degree in science in mathematics and astrophysics at Australian National University. He undertook another year of postgraduate work on accretion disk around black holes, then sidestepped his academic career to allow independent study of automatonic physics. This journey has brought Nigel to the fascinating topic of exploding dark islands. So I give you Nigel.
Thank you very much, Ralph. Right, well, good morning, everybody. Thank you very much, Ralph, and welcome to Ancient Orvonton and a Young Cosmic Web. That was the blurb from the last one. That's right.
That's right.
Now, back in 2016, as Ralph just mentioned, I tried to say something about the sort of physics that would allow dark islands to explode. It was a very feeble attempt, so in the next 2 years, I reworked all those ideas into this series of YouTube videos. For those who haven't seen them, in this first part, we look at the Urantia book's unique and completely new foundations for physics, and see how so-called dark mass emerges from condensates of space potency. In part 2, we put ultramatonic foundations under the Standard Model and see why Dirac's model for the electron and a Higgs-type mechanism work so well. And in the third one, we look closely at what happens when the neutrons in a neutron star start to melt, and why those dark islands, or stellar mass black holes, eventually tend to explode. For those who've seen the videos, I think you'd agree that the Urantia book tells quite a tale about mass and matter and dark islands that explode. Central to this story are these new foundations for reservoirs of energy and invisible mass that science currently can measure but can't explain. This is especially relevant for astronomy. So in this morning's session, what I'd like to do is to test drive this very big script, which is going to be eventually the missing fourth and final part of this video series, in which we'll be exploring what these new foundations might mean for the Milky Way, our home sector in an ancient superuniverse. First, I should mention that the authors of the Urantia book view the cosmos from outside time, which means they can say some interesting things about eternal purposes and transcendental causation, and even Einstein's spooky action at a distance. But this also means that any sequential time-dependence history that they reveal must involve ambiguities and compromise. Nevertheless, they explain that reality really does involve a crucial finite phase of time-dependent evolution. It's this finite or time-dependent side of Urantia book cosmology that we'll explore in this fourth and final part of our introduction. Now, for those who may be wondering how all this physics fits in with the main message of the Urantia book about meanings and values, we try to cover meanings and values back in the first 3 parts of this series. And here you can see where this morning's final component to this whole set fits in. Those are the three that I mentioned earlier on. They're all up on YouTube, ready to go, and there's some pretty dense technical stuff in there. And this is the fun stuff where we can think about stars and black holes and things like that. Right. Okay. In telling their time-dependent story of the cosmos, the authors distinguish between two distinct components. One is ancient, organized, and relatively small, relatively very small. The other is impressively vast and possibly quite young. This small part they call the grand universe, a massive disk-like structure at the center of enormous nested levels of outer space. Taken together, these two components, this ancient tiny kernel and these vast levels of outer space, form the so-called master universe. This distinction between an ancient, organized grand universe and unevolved levels of outer space is so unorthodox that our first step is really just to try and get a feel for the sort of story the Urantia book actually reveals. And straight away we bump into a problem. The authors themselves throw cold water over our expectations. Quote, "Within a few short years, many of our statements regarding the physical sciences will stand in need of revision." Will stand in need of revision. These papers were written in 1934, thereabouts, and clearly many of those, quote, statements regarding the physical sciences simply echo scientific ideas of the day. But anyone who reads this section will have to wonder which of their more interesting scientific statements represent, quote, authoritative elimination of error, or, quote, otherwise earned knowledge. In fact, it was my motivation for making this set of videos was this carrot they left dangling, the possibility for authoritative elimination of error and for otherwise earned knowledge. In other words, as we read these papers, we should be on the lookout for, one, hints about where native physics has gone wrong, and two, insight about things beyond human capacity to prove, and thus possibly otherwise already earned. With this in mind, let's see what we can discover about Orvonton, our ancient superuniverse. Now, here's the plan. First, we'll look at what the authors mean by the grand universe. Next, we'll try to put this grand universe into some kind of astronomical context. Then, regarding the Milky Way and Orvonton, we'll compare what astronomers actually see with what the papers say. One thing we'll find is that the story of Orvonton involves an awful lot of time, much more than 14 billion years. So we'll also look at how a simple idea about redshift has led cosmologists to believe in a young universe, beginning with a hot Big Bang. First, the grand universe. Paper 15 opens with the following scene: eternal central Havona, surrounded by the superuniverse space level. Now, somewhere, this is not verifiable, I think somewhere in the archives of Havona, there's going to be an entry which reads something like this: "And 7 small teams of ancients of days stepped out." In this unorthodox Urantia book cosmology, history, the time-dependent story of the universe, literally begins when 7 small teams of ancients of days step out from eternal Havona into space-time, into the shallows of this, I see it as a continental shelf, the superuniverse rim of this grand universe wheel. Question is, where did they go? Because wherever those 7 small teams went, those 7 places in space mark the centers of rotation for 7 superuniverses. From the start of paper 15, quote, the first post-Havona creation, meaning the superuniverse space level, was divided into 7 stupendous segments, and the headquarters worlds of these superuniverse governments were designed and constructed. Now, just to clarify, here they're talking about the first post-Havona creation. At this stage, there aren't any galaxies in outer space, so no cosmic web. That's worth keeping in mind. But here's the good bit. Again, from the start of paper 15, quote, the 7 master spirits radiate their influence out from the central isle, thus constituting the vast creation, one gigantic wheel. The hub being the eternal Isle of Paradise, the 7 spokes, the radiations of the 7 master spirits, the rim, the outer regions of the grand universe. The hub, the 7 spokes, the rim, the superuniverse rim of the grand universe wheel. This is how paper 15 introduces the grand universe as 7 sub-centers of rotation in orbit around Havona. That's the sort of picture that I think is the simplest way for me to interpret the way they've started paper 15. That there are in fact these locations in space, these headquarters, these capitals of these 7 superuniverses. Lots of questions about how these creations, how these superuniverses are separated, but that's all for another day. Okay, now I should emphasize, this is not the scientific method. This is not a mathematical model based on data and facts. It's just a very literal and simple sketch of a simple, unorthodox idea presented in paper 15. On the other hand, if we're going to have the gravity of paradise acting on an isolated rotating ring of emergent energy for a few trillion years, then maybe something like this is what we should expect. Again, there's no, at this stage, there's nothing much to look at beyond this. This is still the grand universe age. So I'm in this picture, I'm distinguishing between the grand universe age, which is what's the focus of attention here, creative effort, evolutionary hard work, and the master universe, the outer space levels. I think, I'm happy to leave that as being not quite there yet, because the idea of this being trillions of years worth of activity, that's a staggering idea to think that the grand universe, structures in the grand universe, are described as being measured, being evolved for trillions of years. That's unheard of. Anyway, so that's paper 15. That's how things get started. Right. But think about it. The 7 master spirits imposing characteristic systems of energy and mind on their slice of this grand universe wheel, exposed to the distorting tidal influence. I've lost the distorting tidal influence of paradise. Exposed to the distorting tidal forces of the source and center of cosmic gravity. So this central region of creation is exposed to extraordinary energies and forces. And if you know any general relativity, the whale curvature is going to be squeezing these things. That's my excuse for doing this teardrop sort of effect. Anyway, that's sort of for a technical future. Right. Now, a feature of this scheme, as you can see, a feature of this scheme is that, there we go, it makes the grand universe flat, because the idea was that these 7 teams of Ancients of Days have gone out from Havona. Oh, yes, I think we're about to see it. I haven't got a 3D fly-through ready yet. That's upcoming. Dave's motivated me to get that in place. A month ago when I said we need to do this, I'll get Blender, I'll make it happen. It took me a long time to make anything happen. So I said, but we'll leave that till after this session here. But I did make the first, I think I can switch across to, just take a note of that page there, that's image. That image we can simply drop into Blender and play with it. So there it is again. And you can see the idea that I'm proposing is that that whole grand universe wheel is in fact a grand universe wheel. It's flat. So from above, there we are. And as we mentioned last night, Dave's fabulous fly-through, I couldn't help but notice when I first thought about this, but that central universe, they're all coplanar, those billion Havona worlds. So from the side, it's one world thick. That got me thinking about things. I can turn off those dark gravity belts, I believe, yeah? Paradise isn't in space, so I'll turn Paradise off. And there we have it. A bit like Saturn's rings. When you fly through Saturn's rings, they disappear. So this is part of the model I'll be working on for the next, till the day I die, that this inner kernel for the master universe. If you think about what the grand universe represents when it's finished, perfected, end of the grand universe age, a stable central kernel for the master universe. So I'd like to model it as being flat. Anyway, that's future work there. Thanks, Blender. Thanks, Dave. Now, there we are, right. Right, sorry for that little diversion, but it's a fascinating thing. Once you start with 3D modelling, then you can't stop. You come out a month later and haven't made much progress. All right, so I'll just get back to that little bit about when looking at from the side, this central universe in this model is going to be just one Havona world thick, if you rotate it. And likewise, as we'll see, as I'm going to try and make a case for, by aligning the seven super universe systems in the same shared super universe plane, we can make the entire grand universe the thickness of one spiral galaxy. I'll see if I can convince you of this idea I've got an hour to do that. Okay, right. One more thing about this, where we're up to. In paper 23, there's a strange, it's pause to consider, yes. It's worth considering that the central universe is one world thick. Now, in paper 23, there's a strange comment about direct travel between super-universe capitals. From paper 23 to 15. Solitary messengers are the only available type of spirit intelligence, aside possibly from the inspired Trinity spirits, that can be dispatched from the headquarters of one super-universe directly to the headquarters of another. All others have to go the long way round via Havona. That intrigued me. What is it about the separation of these 7 substructures that makes it either impossible or inappropriate for, shall we say, finite beings to move in between these super universes? The thing which I mention this because these 2 types of beings, solitary messengers and inspired Trinity spirits, are said to maintain, quote, an organic association with the transcendentalists and the architects of the master universe, which for me raises the question, are these 7 super universes isolated not just in space, but also in some more transcendental way? And again, it's just something to consider. I mean, there's a lot of complications here. Very simple introduction, a little sketch, but there's a lot behind, When you read paper 15, paper 32, it goes deeper and deeper and deeper, as all the other papers do, when you read it the second or a third time even. Right. Of course, the big question here is, can we connect a scheme like this with what astronomers actually see? Well, fortunately, the groundwork may already have been done for us. As we're about to see, astronomers have mapped out what looks like an ideal place in space for us to put this sort of grand universe wheel. In 2014, astronomer Marshall McCall presented a study of an apparent ring of 12 galaxies, to which he gave the catchy name, a Council of Giants. As you can see, the Milky Way and Andromeda are near the middle of this ring, just off the centre. Now, the surprise here, and the point of McCall's paper, was that relative to each other, his 12 giant galaxies seemed to be bound together, as if holding formation in this persistent elliptical ring. Relative to each other, there's no relative motion. They're actually sitting there as a ring, so that the red shifts and the blue shifts, all of that, imply to him, and that's why he wrote the paper, that this is a phenomenon. That ring of galaxies aren't sort of dispersing. It's as if they're held together. Right, now to native astronomers, this Council of Giants is just one of those things, a chance arrangement due to gravity. But in a Urantia book scheme, it may be something more. In paper 32, section 2, the author states that our place in the Milky Way is well out towards the edge of Orvonton. That's from paper 32, section 2. Now, in the Urantia book, all references to Orvonton are associated with the Milky Way. So it seems natural to associate Orvonton with structures in here, close to the Milky Way, and not with galaxies in this more distant ring, let alone Virgo supercluster or Hydra Centaurus. But just it seems more reasonable to create a suns and ancients of days, a slightly more dense grand universe than has been proposed in the past by Urantia book students. Also, if Orvonton is going to span 1/7 of the super-universe rim of the grand universe wheel, as we saw earlier, then it's tempting to put this grand universe wheel right about here. Its ragged edge running something like this, which would make Andromeda one of those objects, quote, on the fringe of Orvonton and travelling along with us. And it would make this persistent elliptical ring, McCall's Council of Giants, a boundary. The inner fringe of the first of those nested levels of outer space, what astronomers now call the local sheet. Now, for those who want, if you've looked at this before, I'm sure some of you have, there's an issue of the alignment of the Milky Way's plane, the plane of the Milky Way's disk, and the plane of the local sheet. Well, to get around that little issue, I'm proposing imagine a multi-gimbal gyroscope. For stability, I think of the outer space levels not only rotating around the grand universe, but also precessing and nutating over. So there's multiple motions. I won't mention multiple dimensions, just multiple motions. And so that sort of reinforces the idea of the grand universe as a stable central kernel for the future master universe. So what's missing from this picture? To make this plot more realistic, more consistent both with current theory and with the Urantia book, we need to add something that we can measure but can't see. A distribution of mass energy, halos and dark disks of something invisible but full of energy and thus mass and thus mass, and thus gravitational response. Now, about these halos and dark disks, back in part 4a, the first of the cosmology series, I mentioned a famous disagreement between two predictions, one from particle physics and one from cosmology, to do with this distribution of energy in space. Since this is central to our story, I'll repeat the highlights. Now, cosmologists tell us, there we go, cosmologists tell us that for their models of the universe to work, space needs to be mostly empty. But particle physicists tell us that to make their quantum field theories work, space needs to be surprisingly full, implying some enormous energy density filling all space. And as we saw in part 4a, the Urantia book resolves this by localizing the distribution of energy as isolated energy-dense cyclones of so-called segregata, or pure energy, and as invisible rotating superfluid disks of emergent ultimata, and in which these visible galaxies of gravita. Those are the three terms when they talk about the evolution of mass and matter in the papers. We've got space potency, or absoluta. The first set of force organizers catalyze or condense segregata out of the space potency. Their associates, the transcendental master force organizers, inject angular momentum effectively. They actually get the whole thing going. And finally, gravita is just the term they use for standard model particles. Right, now for the expert, right, now this is exciting stuff. For the experts, I had to throw this in. I think this is where we'll find Frank Wilczek's axion. Most dark matter searches, if you're interested in that sort of thing, have cost a lot of money and produced no results. But there's, like Bohm's pilot wave, there's still one candidate really left for this dark matter, and that's Frank Wilczek and his axion. Now that's a long story, technical stuff for the future. But I just thought I'd mention that because this could be, he's the ideal sort of guy for us to set up an interaction with. All right, so for more on this, see that first video, that's part 4a. Okay. Right, so in these empty places between islands of pure energy, cosmologists find the sort of emptiness that they need. But in here, within this grand universe wheel, this proposed grand universe wheel, where quantum field theorists have their labs, we find the sort of density of energy that their quantized field theories predict. So here we bump into our first real twist in the standard cosmological tale, this energy-dense grand universe wheel, an island continent of pure energy at the very center of space, ancient, organized, and inhabited. Exactly what we need to make sense of the Urantia book's unorthodox cosmology. As we'll see, this revelatory background allows us to tell a much more interesting story about our spoke in the grand universe wheel and about our ancient spiral sector of stars, the Milky Way. But first, let's see what the scientific method has revealed. What do we actually know about the Milky Way? Back in 2010, National Geographic released a really excellent documentary, 2-hour documentary, inside the Milky Way. And this brought together everything we then knew about, and assumed, about our home system of stars. To help set the scene, here's a 60-second clip from that documentary.
The Milky Way, we believe, is a spiral galaxy. So what we're really seeing when we look up at night at this band is we're seeing our place in the universe. We're part of a giant disk of stars.
That's just an insider's view.
Now, of course, I can't show you a picture of the galaxy in all its glory. We can't fly above the galaxy and take a picture of it and show you. We're stuck in the disk of the galaxy, but we can still image it from the ground. In fact, this image is a picture of our galaxy, the Milky Way, taken from Earth. Perhaps the most beautiful part of this image is that we have this contrast of dark and light regions running through the plane of the disk. What that really is, it's dust. There are clouds of dust that are casting a shadow from the back of the stars. So the stars are trying to shine their light through. There are dust clouds there that are blocking the light, much like a cloud on Earth would block the sun.
Sorry about that. Did you hear that?
Yes.
Okay. Right. Now, about these clouds of dust and gas, what we see depends on how we look. So when using visible light, like the Hubble Space Telescope or the Keck ones, the large optical telescopes, we see something like this, which for poets or philosophers might be just fine. But for astronomers, it's really frustrating. Until recently, astronomers had no way to see through all this dust and gas, so it was famously, they avoided looking at this entire part of the sky. They would find some better place to look to see the universe, because this whole section of the sky was blocked, and thus it became known as the zone of avoidance, famously known as, right, because they literally avoided looking in that part of the sky, unless they were studying dust. But in 2003, NASA, thank God, launched the Spitzer Space Telescope. And Spitzer was built to look in the infrared. In astronomy, what we see really does depend on how we look. And this is what we see when we look at that zone of avoidance in the infrared. Actually, this is the far infrared. More famous, even better, is the near infrared. That's 1 to 5 microns, that sort of wavelength. At these wavelengths, all that dust and gas becomes transparent, and we get a better view of the actual distribution of stars. Now, we've known for some time that this belt of stars is at least 100,000 light years wide. What's not so well known is the actual distribution of stars within this disk, which turns out to be surprising. Astronomers now estimate that up to 95% of all the Milky Way's main sequence stars lie in a thin disk less than 1,000 light years thick. Again, for the video, the final version of this, there'll be a proper 3D fly-through to make it interesting. But for now, if you reflect on those two numbers there, it's 100,000 wide, 1,000 thick, the main distribution of stars, 100 to 1. So if you think of millimeters, that's 10 centimeters by 1 millimeter. That's a DVD. Yeah. So the geometry of this thin disk, the bulk of the distribution, most of the stars in the Milky Way are sitting in this structure that is a bit like a DVD. So you turn an edge on, and it's very, very thin, very, very thin. We think of it as being a bit fluffy because there's a lot of dust and local stars, but once you start to study this sort of stuff, it's extraordinary how thin spiral galaxies can be. And it's the same principle as Saturn's rings. Gravity and angular momentum will drive things into a plane as they're orbiting around. Fabulous stuff. Great to simulate on home PCs now. Okay, so what would this system look like from above? Here we have a problem. Astronomers have worked out that our sun sits about 26,000 light years from the center of our spiral of stars. However, it's right in the middle of the dense mid-plane of the disk, and as James Bullock said, you might remember he said something about this, we can't just fly up above the disk like a solitary messenger to get a bird's eye view. So, as we're about to see, this is a beautiful little bit here. trying to map the Milky Way is a bit like a little bit of pepperoni in a really, really big pizza, really big, really thin, trying to map the pizza in which it's stuck. Now, Bob Kirshner, here he explains it here.
Something like a pizza, and if you were in the pizza, if you were a pepperoni, your view would not be a very clear one of what the whole story was. In the same way, we don't see the whole reach of the Milky Way.
What astronomers really need is a bird's eye view.
You would need to get out of the Milky Way to really see what it looks like. We don't have a way to do that, but we can look at other galaxies and see what they look like.
So that's where we're up to. We look at other galaxies, we make measurements as best we can, and we then extrapolate and assume that we're just another spiral galaxy, you know, just isolated. Now, right, so by looking at other galaxies, by trying to map the Milky Way's spiral arms, astronomers now think that from above, the Milky Way would look something like this. Our sun, about here, and here's that center of rotation, about 26,000 light years away, that we call Sagittarius A star. To estimate these distances, 26,000 light years from the sun to the center and 100,000 light years wide, astronomers have a toolkit of techniques. In paper 41, referring to this toolkit, the author states, quote, "By this technique," referring to Cepheid variables, "it's possible to measure stellar distances most precisely up to more than 1 million light years." So back in 1934, the author was just pointing out that yes, with your tools that you've got, you know, no problem, your distances, what this implies is that our current measurements of distance within the disk, within the Milky Way, are on track. In particular, this distance, 26,000 light years to Sagittarius A star. Okay, so far so good. Now, does the Urantia book say anything interesting about this system of stars? Oh yes, it does. It says that the center of our minor sector is over here. Feel free to make comments if you've got other ideas about this, but one, I think the simplest way to fit this together is to assume that, I'll just read the quote about this minor sector. "The rotational center of your minor sector is situated far away in the enormous and dense star cloud of Sagittarius, around which your local universe and its associated creations all move." And if by star cloud of Sagittarius they mean Messier 24, about 11,000 light years away, and if this dense star cloud, this single dense star cloud, is the center of rotation for our minor sector, then Sagittarius A star becomes an obvious candidate for the center of rotation for our major sector. Sagittarius star cloud, that's an interesting astronomical phenomenon. They say it's more of a tunnel that we can see through, but in 1934 it looked like a very dense cloud of stars. Anyway, that's the star cloud of Sagittarius. But in the next couple of lines, just have another look at what they say. Again from paper 15, section 3, quote, "And from opposite sides of the vast Sagittarius subgalactic system, you may observe two great streams of star clouds. Two great streams of star clouds emerging in stupendous stellar coils." So notice, two great streams of star clouds. The authors appear to connect our minor sector, ENSA, with a single star cloud. Then appear to suggest that our major sector, Splandon, is centered somewhere between those streams of star clouds uncoiling from Sagittarius A star, all of which seems reasonable. But then they say something weird. from paper 32, section 2, quote, from Gersum, the headquarters of Satania, it's over 200,000 light years to the physical center of the superuniverse of Orvonton, end quote. 200,000 light years. That's another 174,000 light years past Sagittarius A star. In other words, way over there, way off to the right. Let's try to put that distance in context. Once again, from paper 32, section 2, from Gersum, the headquarters of Satania, it's over 200,000 light years to the physical center of the superuniverse of Orvonton. And from the same paragraph, from the outermost system of inhabited worlds to the center of the superuniverse is a trifle less than 250,000 light years, end quote. But hang on. In this story, Uversa is supposed to be a center of rotation for eventually the 10 major sectors of a superuniverse. How can we make this work? Well, in that same section, the author also states, quote, Nebadon is now well out towards the edge of Orvonton. And here's that distance again, 250,000 light years from the edge of Orvonton to Uversa. But back in paper 15, section 3, they say that the length of this superuniverse, is far greater than the breadth. Do they mean something like this? The local universes are in closer proximity as they approach Havona. They also state that on the Havona side, local universes are more tightly clustered and, quote, layered, layer upon layer. Are they suggesting a distribution something like this? Increased density on the Havona side. The circuits are far greater in number and there is increased superimposition, layer upon layer. All right, so that's again just what they're saying about this superuniverse. But what about those 10 major sectors? Again, from paper 15, section 3, quote, if you look upon the superuniverse of Orvonton from a position far distant in space, you would immediately recognize the 10 major sectors of the 7th galaxy. About this term, 7th galaxy, throughout these papers, galaxy is used as the collective noun, as in galaxy of stars, or galaxy of gods, or galaxy of creative personalities. So if we read galaxy as galaxy of major sector spirals, which we would immediately recognize, are they suggesting something like this? But then again, in paper 12, section 1, the author implies that this 7th galaxy of major sector spirals is, quote, as yet uncompleted, which makes me wonder, is the Andromeda spiral actually one of Orvonton's future major sectors slowly sliding into place? It's just a cute little idea, that. Had to do that. Of course, nothing in native astronomy or cosmology predicts anything like this. But as a thought experiment, let's ask the question, if this spiral of stars were here, could we see it? Remember, almost all the Milky Way's hundreds of billions of stars lie along its mid-plane within this thin disk, about 1,000 light years thick. So in paper 32, when they mention that, quote, dense diameter of the Milky Way, think of this thin red band. Now, imagine we could bring Andromeda 10 times closer than it is. Place it, say, 200,000 light years behind the Milky Way. To get a better view, let's switch to infrared. Okay, if such a nearby giant spiral was spinning face on to our line of sight, well, it'd be very, very easy to see. A monster. But if we tilt this neighbour to be edge on, its profile in all wavelengths becomes a faint echo of the foreground Milky Way, so that when we drop it down into the plane of the Milky Way, its profile becomes, well, vanishingly faint. A vanishingly faint echo sitting right behind the dense diameter of the Milky Way. So here's the question. Using existing telescopes, if such a neighbour existed, could we see it? This is assuming this idea of the grand universe being flat. Ancients of days going out from Havona, in that grand universe wheel. We happen to be on the outer edge of the grand universe, and when the angle of observation is propitious, where's that from? You're gazing to through the residential centre, the centre of all things. So anyway, this is just one way of teasing out this description. And for me, it's simpler than needing to go and look for major sectors in the Virgo cluster, or something more bizarre or elaborate. If we're going to have paradise and superuniverses, I think this is the neatest way for us to approach the problem, and then to look at this from a scientific point of view, which, if I survive to the end of this talk, I'm ready to dive into the data and start mining it and see if we can find any anomalies in there. Oh, hang on, more's to come. What about this? A set of spiral galaxies. What we have here is a Urantia galaxy. In other words, a galaxy of major sector spirals, a collection, the seventh collection, the seventh galaxy of major sector spirals. It's a long leap. I'm drawing a long bow, but I'm throwing it out there. Now, imagine they're all tilted, right? They're all going to be in the same grand universe plane, or superuniverse plane, all tilted to be edge on, all lined up directly behind this dense diameter. Now, the James Webb Space Telescope, one hopes, will eventually launch. Has anyone been following the saga? Should have been up a couple of years ago. It's going to get there, it will get there, and it's optimized for finding major sectors behind the dense diameter. It's just the tool we need. So that's just a lovely little moment there. Just allow this idea to just sit in the back of your mind, that if these other sectors, major sectors, were in fact coplanar with the Milky Way, behind the dense diameter, it may not be so easy to see them. Now, keep in mind, this is still just our thought experiment. There's no scientific reason or data yet to suggest that a system like this exists. For me, this is just the most literal and the simplest, way to model what the papers seem to say. With this in mind, let's take the next step and see where this thought experiment leads. Clearly, a system like this implies architecture and organisation, both of which the Urantia book describes with its master architects and force organisers. And as we saw in previous videos, the earlier videos, that's parts 4A, B and C, these papers also provide the sort of extended standard physics that such a scheme requires, adding to this picture three essential but invisible or dark parts. One, that vast swirling cyclone of massive ultimata, out of which this gravita has been evolved by the power directors. So ultimata, that's a sort of an ancestral substance out of which things like spiral galaxies get built or evolved. So, first one is this vast swirling cyclone that's going to be rotating. This is not your average spiral galaxy, but remember, this is not the outer space levels. This is the superuniverse space level. It's a different mode of creation, as they tell us a few times. Right, so I'm proposing this pool of ultimata. The superuniverse is embedded in this ancestral dense medium, invisible, dark mass. And number two, that ancestral halo of segregata, or pure energy, a locally localized Higgs-type field. And three, and most importantly, the tidal effects of paradise. The tidal effects of paradise, the universe's source and center of gravity, acting for a very, 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 very long time. Question is, could this sort of extended standard physics explain the evolution of a system like this? Well, let's have a look. Think how ice is less dense than water, how icebergs, enormous mountains of ice, float and get carried along by ocean currents. Now, think of these spirals of stars, these disks of gravita, as icebergs in a flow, a vast superfluid flow, not of water, but of superfluid ultimata. Superfluid meaning no friction, just flows and keeps flowing. So these visible galaxies, these iceberg spirals, will naturally go with the flow, carried around Uversa, not just by gravity, but also by ancient, force-organized flows. Now, if we float this whole system in a cyclone of segregata, pure energy, then what we have here is a completely unexpected distribution of energy and mass, and thus gravitational action and response. Within such enormous energy-dense flows, these little spirals of stars would get carried along like so much fluff. Gravity is a very small actor in this setting up this structure in the model I'm proposing. These are the flows of these ancestral, dark, massive, energetic media, emergent media. The thing is, this sort of story actually fits in. Do I need to go to the next slide? No, right. This sort of story actually fits in it fits in very well with current mainstream speculation. What we have here are spirals of stars evolving in dark superfluid disks nested in halos of some mysterious invisible condensate, which is exactly what cosmologists are discussing at their conferences right now. In fact, there's probably at the University of Chicago, they're probably talking about this right now. To get galaxies, spiral galaxies, to behave the way they do, we need two, they think. Easiest way to get it to work is two types of invisible mass, dark mass. One is the classical old version, halos, but another one, you need to get this spiral action to happen, they need something else, and they're proposing a superfluid disk. So I'm just jumping on the bandwagon. This, I'm sort of feeding it into their mainstream, because this is the way they're talking. And there was a fascinating feed of my little news feed this morning about accelerated expansion. That's another story. So it's an interesting time to be doing this, given that Sean Carroll's gone completely off the beam, etc. And Lawrence Susskind has given up physics. He says they can do no more. They're stuck, completely stuck. All right, now, so this sort of gravitational action on invisible mass is not so controversial. The real issues here are organization and time. Even with paradise architects and force organizers pulling the strings, it would take a long, long time to evolve a structure like this. And when we pop Orvonton into place as the seventh spoke of that grand universe wheel, the issue of time becomes deep in telling the story of this relatively small grand universe. The papers talk in terms of trillions with a T, not mere billions of years. Which brings us back to that point I made at the start. In Urantia book cosmology, from a finite or time-dependent point of view, this grand universe age, this vast span of time and evolutionary effort, applies only along the superuniverse rim of the grand universe wheel. The doings of outer space may have only just begun. Once again, let me emphasize, this is not the scientific method at work here. This is simply a sketch of the sort of story the Urantia book reveals. It's my attempt to see how our local spiral of stars, the Milky Way, might fit in with the idea of Orvonton, and how a truly ancient grand universe might fit in with some kind of reasonable astronomical context. So now the fun begins. How do we connect up this handful of unorthodox and ambiguous ideas to what native science currently believes? So that's the first half.
Keep going.
That's the first half. The way it evolved was, that was sort of, this first chunk is my attempt at a literal rendering of the Urantia book cosmology, the sort of story about the grand universe they make. Not trying to have an opinion about this, just looking at the paper and thinking, well, creator sons, I mean, this is a family affair in the superuniverse. You've got ancients of days, creator sons, local universes, a very organized system. So if we're going to look for minor sectors or major sectors elsewhere, in the vast reaches of outer space, it becomes a little bit, it's going to take a long time to get anything done. The phone call, even reflectivity might not solve that problem. So this is why I said, can we get something local? Can we make some sort of grand universe, literally hidden behind that dense diameter of the Milky Way? So it's completely speculative. But because I've got no academic credentials to support or to worry about, I'm free to dive in. And the survey data now, these archives around the world, the telescopes have been pouring this data down now. And you've got poor little postgrads who get sentenced to sit in the data room or at home on their computer and mine the data and see what they can find. They find interesting things. And that's why this James Webb Space Telescope, it's, we're all chafing at the bit, thinking, because that's the sort of device, infrared optimized, to punch right through this. Do you remember that movie from the previous night? Was it last night? Yeah, that fly through into the Milky Way. That's what they did there. That was a collage. They merged a number of different data sets. And when we got to that point where it looked like there were 3 stars there, and then I paused it, the original zoom just goes straight in, and it gets clearer, fuzzy, clearer, fuzzy, clearer, fuzzy. So it's extraordinary what these telescopes can do now. And that was just an illustration that they can probe right through that dense, the dusty regions, and find at redshift 2.5 that gravitationally lensed quasar. That's what the point of that zoom was. Zoom through the dust and gas. There is a phenomenon. But that was so far below the plane of the Milky Way. It makes you wonder, they don't bother zooming into the middle because it's an infrared line of avoidance, pretty well what we've got. The old zone of avoidance, remember that big zone of avoidance? Well, we've got a similar but much more subtle problem with an infrared line through this dense diameter, which if this idea is on track, if in fact angular momentum and gravity have done their thing over trillions of years, if Paradise has done to the grand universe what Saturn has done to her rings, two-dimensional, then wouldn't it be a fascinating thing if the first thing that the James Webb Space Telescope found well, there's a couple of galaxies lurking behind the Milky Way. Anyway, so that's my motivation. That's sort of, I can't see a problem with it, so I'm carrying on. If I can see that it's hopeless or completely wrong. So that's really the point of this weekend for me, was if I throw this out there and you, Halbert, people on the web, Alex, Dennis, I'd love some feedback. You know, where is this going wrong? What is inconsistent? What seems to hang together? What could be expressed in a better way? That's the sort of thing which you guys, your homework is to poke holes. Now, we've got half an hour. What I've got, this next chunk is really just looking at the redshift issues, Hubble's law and stuff like that. We can just zip through that. That'll take about 20 minutes. So we could finish with that. So how about any particular questions or points you'd like to throw up right now, whilst it's sort of fresh?
Just a second.
I have one question.
Second. Second, I'll tell you when. Okay.
I have a question, Nigel. How good are astronomers at detecting the actual edges of a galaxy like the Milky Way? That is, out there in the fringe, how far out does the fringe go? Because the revelators suggest to us in their description that they can go all the way out to the very edge and even beyond. They know what's out there, and so I'm wondering, when we make measurements of a galaxy, how reliable do you think those really are?
Well, it fades off to nothing. So
Right.
it could, in fact, be that the halos of the Milky Way and Andromeda are touching.
Yes.
This is the invisible components. These halos of dark mass, or invisible dark matter, dark mass, because it's not really going. The case I'm making is that it's like Frank Wilczek's axion. It's a condensate, a superfluid condensate of ultimatons and segregata. So those two types of invisible energy mass, sources of gravitational action, all of these things we can see, all of the gravita, all of the galaxies, very little, they're like little fluff balls in the middle of this really dense background. And so the Milky Way stars, we talk 100,000 light years across, but it goes, there are stars out and out and out, and then very, very wide orbits. And so some of our stars might be sharing with Andromeda and coming back. There's no well-defined edge to that sort of thing. It's still a bit of a... physicists don't really call cosmology a science.
So
It's a little bit rough around the edges still.
Yeah. The reason I raise that question is that the description of the Milky Way that's given to us, first off, appears to be, now first off, the Milky Way, it can mean more than one thing. It can mean that fuzzy, creamy looking band that we see as we look into the night sky. But the other term, of course, the other meaning is the Milky Way galaxy, which is this spiral configuration of stars that we recognize. But the description in the Urantia book suggests that the Milky Way and Orvonton are the same. They use the terminology, like, as you mentioned, if you look at all the references to the Milky Way and you eliminate those that refer to that band appearance and think about the Milky Way in the Urantia book as meaning the galaxy itself, then they suggest that the Milky Way galaxy is the Orvonton superuniverse. And so the measurements, though, don't fit. The astronomical measurements that were given
are much smaller for the Milky Way galaxy than the ones given in the U-book. And so my question is whether or not we might be confusing measurements of different things here, and that we're in fact, the Milky Way is much larger because the fringes are not included in the astronomical data.
Yes, it's that's what I cover. That's what the video is all about.
Really enjoyed your presentation. Thank you. But all the quotes you're reading in the Urantia book, especially in paper 101, where it talks about, I forget the exact phraseology, but it says people might read this cosmology and find one or two errors in it and discard it because they found errors in it. And then it says something to the effect, but you shouldn't throw out the baby with the bathwater because of the associated cosmologies presented. In other words, they use plural, and if you this was something that somebody else brought up, I forget who it was, but that there are actually multiple cosmologies represented. In other words, they when the book was published, there was this, in the transition period from the galactocentric model, where they thought the universe was maybe 300,000 light years wide. And then in 1929, they discovered space expansion, and all of a sudden it was 1,000 times larger. So it was a different model. So when they were writing, this, there were actually two models, and then they throw in their own cosmology. So I think that explains some of the confusion upon reading. If you read it too literally without understanding there are multiple cosmologies represented in the book, because they're not going to just hand it to us on a silver platter. So
I did say ambiguous and unorthodox.
yeah.
Would you like me to just, I think I can fit this next little bit in. This is where we try to make contact with my colleagues. Right. Okay. Yes, thanks, Ralph. That's that whole thing. That's a long, slow discussion.
Yes.
Yeah, it's going to be a round table for weekends and. Right. Well, let's just have a quick look and see what we can do with fitting this into an astronomical context. Mainstream cosmology currently sits on a few simple assumptions about Hubble's law, about redshift, and about the universe beginning with a hot Big Bang. Taken together, these ideas lead to models like so-called lambda CDM and to predictions about the age and history of the universe. So where did all this come from? The idea of a Big Bang, these finely tuned models, these estimates of universe age. It began with the slope of this line. By 1929, astronomer Edwin Hubble had worked out rough estimates of distance to about 24 nearby spiral galaxies. When he plotted these distances against redshift, he noticed that the distance to these spirals might be proportional to their redshift, which for astronomers would be huge. They could find the distance to a galaxy simply by reading its redshift. That was their hope. As to what was causing these redshifts, Hubble himself remained non-committal. Not so Georges Lemaitre. Lemaitre, another astronomer, jumped on Hubble's data as evidence that these spirals were all racing away, that their redshifts were a simple Doppler shift caused by their speed of recession. In fact, it was Lemaitre who wrote down Hubble's law, that redshift reveals velocity, and that velocity, the apparent speed of recession of spiral galaxies, is directly proportional to their distance. This constant of proportion, Hubble's constant, or h0, is given by the slope of this line. Lemaitre's idea was that the entire universe must be expanding, as if growing from some original cosmic egg. Now, given that Lemaitre was a Catholic priest, and that his cosmic egg, this prototype Big Bang, was a bit like some creation myth, and that Hubble's data was a little bit rough, many, including Einstein, thought that Hubble and Lemaitre had jumped the gun, that Hubble's so-called law was more leap of faith than real science. Nevertheless, by 1933, around the same time these papers were being presented, this idea of an expanding universe had caught on, and the rate of this expansion is given by h naught, again, the slope of this line. And sure enough, as the data improved, it really did look like Hubble and Lemaitre had been on the right track. As we can see from this recent plot, the data do seem to fit nicely with Hubble's original idea that redshift might be proportional to distance. But notice, this is a plot of redshift versus distance. There's no mention of velocity. The idea that redshift is proportional to speed of recession or a rate of separation is an assumption in a model, an assumption that cosmologists like Lemaitre have to add. But once we accept these assumptions and add a little fix near the start and another little fix near the end and calculate a so-called Hubble time, we get this story that cosmologists currently like to tell, which goes something like this. Given one miracle, one miraculous moment of cosmic inflation, and two little assumptions, we can predict that the universe began to expand about 13.8 billion years ago. Now, about this story, there's a joke that physicists like to tell. Now, cosmologists are always wrong, but never in doubt. So, two little assumptions. Two little assumptions about redshift and rate of expansion. Assumptions which nowadays seem so obviously true that some cosmologists no longer see them as assumptions, but as hard facts that their models must obey. So it's no exaggeration to say that this story, this proposed expansion history of the universe, sits on these two assumptions. So in 2015, two physicists, not cosmologists, Harry Ringemacher and Lawrence Mead, took a close look at these assumptions and this story and the best data of the day. And they noticed something subtle in the supernova data, that the rate of change has been changing every 2 billion years or so. In their paper, they proposed a simple Big Banged universe was in some sense ringing or oscillating as it expanded, that over the last 13 or 14 billion years, the rate of expansion of the universe has sped up and slowed down 6 or 7 times. So in the data, they've noticed a periodicity of 2 billion years for some sort of adjustment to the nature of this expansion. They're just physicists. They just looked at the data and said, "You guys are much good." I don't think he was really rude to the cosmologists, but he did say that some of their methods were a bit flawed, and some of their assumptions were a little bit wobbly. Anyway, so the Urantia book takes this unorthodox idea one more step. It proposes cycles 2 billion years long of gentle oscillation, a so-called space respiration. So paper 11, section 6 is all about that. But getting back to the mainstream, this current consensus model, this assumed expansion history of the universe, is in effect defined by that Hubble parameter, h, as a function of redshift or age. So predicting its current value, the rate of expansion now has become a crucial test. Does this model really reflect universe history? This is the reason that so much effort has been spent trying to pin down a value for h naught. And over the years, estimates have been converging towards about 70 of these Hubble units, that's kilometers per second per megaparsec. But cosmology can be a tricky business. By the 1980s, the simple idea of an expanding universe had become a Big Bang model, very finely tuned and fragile, and inconsistencies had appeared, like galaxies seeming to be older than the universe. In fact, by 1992, rumours were going around about the death of the Big Bang model. But then, cosmologists got their first real taste of this. This is the cosmic microwave background, or CMB, the signal which saved the Big Bang. Almost every feature in this extremely filtered plot, they had to do a lot of work to get this plot out of the data, but almost every feature could be made to fit so well with Big Bang expectations that this cosmic microwave background is now seen as a smoking gun, actual proof that the universe began with a hot Big Bang. After all, if the CMB is not a redshifted surface of last scattering, well, what else could it be? That's sort of where they're up to. Of course, well, in paper 42, they make a suggestion. Throughout all organized space, there are organizing electronic energies. The microwave background, it's electromagnetic radiation. So all that we need is some phenomenon, or some phenomena, to emit, from each cubic meter of space, a couple of microwave photons. And that would remove the need for a Big Bang. Not a big ask, and there's plenty of alternatives sitting in the Urantia book for providing this background signal. This paragraph, presented in 1934, raises the possibility that the microwave background is not a surface of last scattering from some Big Bang, but simply one of the many interesting properties of pervaded space. But hang on, if the microwave background, this non-zero temperature of space, is not a redshifted surface of last scattering, then what happens to that smoking gun? That signal which saved the Big Bang? Hold that thought. For now, putting aside this unorthodox, ambiguous alternative, this cosmic microwave background has allowed cosmologists to build and to polish up a consensus model for native cosmology, so-called lambda CDM. So here, lambda means something like Einstein's cosmological constant. CDM is cold dark matter, and adding a few bells and whistles, we get this standard model. But just when cosmologists thought they could relax, we got this. Damn. Using direct measurements of standard candles, like Cepheid variables and supernovae, estimates for H0 have converged to a value somewhere above 73. This is the rate of expansion of the universe. But as this lower red curve shows, using Big Bang models, not measurements, but models, and the microwave background, estimates have also converged, but to a different value. From observation, astronomers calculate that H0 must be at least 73, but cosmologists, using their best models, require 67. Two of the most sophisticated, carefully calibrated, checked and rechecked estimates of the central prediction of current consensus cosmology appear to have diverged. Latest results are only compounding the problem. So for cosmologists, this divergence has become so unsettling that earlier this year, July 2019, the folks who run the surveys and write the papers which shape current cosmological theories and ideas, they got together in Santa Barbara to try and sort things out. Here's a snapshot from the conference. Adam Rees, Wendy Friedman, Lisa Randall was there, I believe, and Natalie Volchova, fabulous journalist, great science writer. Right, so they were all there, and they were just getting a feel for how they can sort of step around this problem. Now, over lunch on the first day, some of the attendees were talking about how to classify levels of disagreement. If you've got groups working, they disagree, how do you classify these levels of disagreement between model predictions? Sylvia Galli from the Planck satellite team compiled this list. The point being that the disagreement between model predictions for H0 is now greater than 5 sigma, which brought to mind a moment from earlier in the day. This was July this year in Santa Barbara, over in Chicago. I came through Santa Barbara. Things were proceeding as things do at cosmology conferences when some guy over in the corner, front row, pointed out that in his field, particle physics, when researchers have a discrepancy this big, they declare a crisis. This is David Gross. He's the director of the Kavli Institute for Theoretical Astrophysics. There he is. Right, so here we have a couple of apparently incompatible predictions from our current best fit model for the history of the universe, prompting one researcher to sum up the situation like this. It looks like we're going to have to learn something interesting in order to figure this out. As we're about to see, the Urantia book suggests something interesting. But first a comment. Each of these predictions comes from an attempt to fit data to a lambda CDM hot Big Bang model. But if the underlying model is wrong, or not even wrong, then these finely tuned parameters, the finely tuned parameters of that model become like epicycles, helping to fit an erroneous model to increasingly inconvenient facts. So what does the Urantia book suggest? It suggests 2 large-scale motions of space. First, cycles 2 billion years long of gentle oscillation, a periodic expansion and contraction of all space, which the papers call space respiration. Yeah. And second, the counter-rotation of nested levels of outer space. Okay, but can rotation and gentle oscillation explain the systematic, distance-dependent redshifts that astronomers actually observe? And what about that microwave background? Well, they're good questions. Let's see what the Urantia book has to say. When should I stop? Do I have to stop it? I think I can get most of the way in 5 minutes. Let's see what the Urantia book has. First, look, we'll begin with Hubble's law. If Hubble's law were true, then this plot says if we find a galaxy with redshift of 0.16, then we can simply read a Hubble diagram to find out that that galaxy must lie about 2.2 billion light years away and be receding at about 50,000 kilometers per second. In other words, about 30,000 miles a second, a speed which might sound familiar. From paper 12.4.14, quote, "It will appear that these far distant systems are in flight from this part of the universe at the unbelievable rate of more than 30,000 miles a second." At this unbelievable rate. What does the Urantia book say about this, quote, unbelievable rate, this apparent speed of recession? But this apparent speed of recession is not real. This statement is not presented as a hypothesis for us to test. It's presented as a fact which the author is in a position to know. They go on to explain that beyond a certain distance, this redshifting of spectral lines becomes, quote, wholly unreliable as a method for estimating distance or speed. Which brings us to those limitations of revelation discussed in paper 101 section. In section 4, the authors explain that with regard to science and cosmology, they were not free to say too much. Like that prime directive in Star Trek, galactic civilizations don't interfere with developing cultures. However, they do say that if we're barking up the wrong tree, they can tell us that's the wrong tree. From Paper 101, Section 4, while statements with reference to cosmology are never inspired, such revelations are of immense value, in that they at least transiently clarify knowledge by. They then list 5 ways in which this sort of limited revelation can be of immense value. The first goes like this: the reduction of confusion by the authoritative elimination of error. The authoritative elimination of error, but this apparent speed of recession is not real. Is this a case of number 1? The reduction of confusion by the authoritative elimination of error. As far as I can tell, this question of redshift and Hubble's law is the only place in the papers where the authors tell us that one of our scientific assumptions is wrong. Elsewhere, they either echo prevailing beliefs, prevailing ideas like their distance to Andromeda, or reveal things beyond human capacity to prove, like ultimatons. But here, they point to a particular and critical assumption about Hubble's law and tell us bluntly that it's wrong. So what about those redshifts of distant galaxies? In Paper 12, Section 4, 14, the author claims that beyond a certain distance, other effects begin to overtake speed of recession or radial separation as the primary cause of cosmological redshift. Beyond a certain distance, other effects begin to overtake speed of recession as the primary cause of cosmological redshift. So what else could be causing systematic distance-dependent redshifting of spectral lines? Well, let's take a look. In Big Bang models, an assumption is that redshift is proportional both to distance and to velocity. The further away a galaxy is, the greater its apparent speed of recession, and thus the greater the redshifting of its spectral lines. So for a galaxy with measured redshift of 0.16, our current Big Bang model, lambda CDM, predicts that that galaxy must be 2.2 billion light years away and be receding at a rate of 30,000 miles a second. But from Einstein, such a rate of recession implies a relativistic Doppler shift of 0.16. It's this convenient match is one of the features of lambda CDM that with a few nips and tucks it can be made compatible with Einstein's faint glimpse about space and time and gravity. In this sense, this model is said to be a solution of Einstein's equations. But in 1949, a curious character pointed to another, very different solution. The character was Kurt Gödel, and the occasion was Einstein's 70th birthday. What Gödel had noticed was that if the universe were not simply expanding, but also rotating, then funny things would happen to space and time. For example, in a rotating universe, Einstein's equations appear to allow travel backwards in time, so-called closed time-like curves, which cosmologists tend to dislike. Also, a rotating universe implies some kind of center of rotation, which cosmologists really dislike. So Gödel's curious solution remained, like the man himself, a curiosity. A curiosity. But it did get people thinking, what if the universe were rotating? After all, absolutely everything in the universe either spins or rotates. Why not the universe itself? But if the universe were rotating, and if we were near the center, then once again, Einstein has something to say. if that same galaxy, 2.2 billion light years away, were moving not away from us, but sideways across our line of sight, at a relative rate of half the speed of light, special relativity predicts that we'd measure a redshift of 0.16. Same redshift as predicted by lambda CDM. Keeping in mind that these sorts of high redshifts, once you get beyond sort of, a certain distance, the redshifts are enormous, implying huge velocities, but they're velocities of space. So the idea is that space is expanding, not galaxies moving through space at superluminal velocities. So Big Bang cosmology has all sorts of enormous speeds, but it's rate of separation rather than a velocity through space. Okay, do I need to stop?
I don't think so.
Keep going.
Keep going.
5 more minutes. Oh, sorry about that. Same redshift. Both models could give us that same redshift that astronomers measure. You've got a good hard data measurement, a data point, redshift 0.16. But there's more than one way of getting that data point, different models. So speaking about these redshifts, this distortion of spectral lines, the Urantia book writes, quote, "But the greatest of all such distortions arises because the vast universes of outer space seem to be revolving." The claim in paper 12, section 4, is that the main components of the enormous redshifts of quasars and distant galaxies comes not from a runaway expansion of space, but from rotation. Which brings us to the Urantia book's unique idea of nested, counter-rotating levels of outer space. The idea is that entire outer space levels are rotating around our place in space, thus appearing to move sideways across our line of sight relative to us. In paper 11, section 7, these outer space levels are described as curved space paths of lessened resistance to motion, surrounded on all sides by relative motionlessness. Notice at the inner and outer margins, a space level is relatively motionless. So in each space level, we'd expect little or no sideways motion at the edges, rising to some maximum flow midstream, in the midstream of a space level. Now, about motion along these curved space paths, we're not talking about the motion of galaxies through space, but rather the transverse motion of space itself. These are one of the primary motions or secondary motions described of space itself, not relative to. So I'm going to assume that this motion of space is fast enough to be interesting. Now, let's remind ourselves how excruciatingly slow the speed of light becomes on this sort of cosmic scale. Imagine this is a section of the third outer space level, and this dot, this tiny little dot, marks a spot 2 billion light years away, where a telescope finds a Milky Way-sized galaxy. Now, pause to consider. It takes light, travelling at the speed of light, 100,000 years to cross that galaxy. 100,000 years to cross that dot, those few pixels in our best telescope's field of view. What this means is that given current telescopes and techniques, there's no way for astronomers to detect sideways motion of a galaxy or quasar 2 billion light years away. Well, we're going to have nano-lensing of quasar caustic crossings soon, if the JWST gets up there, and there's a possibility for detecting that sort of thing. But as we'll see in a moment, for this galaxy to be going with the flow, cruising along this curved space path, it must be moving across our line of sight at a significant fraction of the speed of light. So given the possibility, I'll just whip through this last little bit, given the possibility of significant sideways speed, of relativistic transverse velocities plus cycles of space respiration, Einstein gives us a simple explanation for the sort of systematic distance-dependent redshifting that astronomers see. So this slide gives us a hint of what's going on. And here's an example of how this could be interesting. And this was in the news feed this morning about reinterpreting the ideas of Type 1a supernova. Big news this morning in the news. Anyway, I won't go through this because this is more technical, but if you had two supernovae, both moving at sideways at the same speed of light, one's much more further away, it's got the same transverse velocity, much more further away, it would appear dimmer, and it might lead, this sort of thing could very easily lead a cosmologist to propose something like an accelerating expansion of the universe due to dark energy. In other words, lambda CDM. This is what I'll be working on this for the, this is my job, this is the next phase, locking this into a model with data that we can present. So let me just, I think I just can sketch to the end. Oh, I've got to show you one last thing. Oh, rats. Some lovely stuff here. I've got to show you what it might look like. The motion of a space level. For another time, that. But here, to get a feel for what this implies, this sort of rate of transverse velocity, the speed of a space level, I'll just show you the sort of numbers that seem to make sense. That galaxy, redshift of 0.16, 2.2 billion light years away, that would give us a circumference of about 12 billion light years. And if you think of, if it's going half the speed of light, it would, in 2 billion years, that galaxy would only travel 1 billion light years. So we get this idea of, it would take 12 cycles of space respiration for that galaxy with a redshift of 0.16 to go all the way around. That's the sort of idea we can model. That's just simply an idea. We can put it into a computer, run a simulation, and see if it's going to generate that same sort of redshift pattern that we want. So that's sitting there. That's primed, ready to go. There's one last thing which I better show you. Right, is there any evidence for this sort of nested levels of outer space? Now this is Cosmic Flows 2, 2014 by Brent Tully's group. What they noticed was these watersheds of supercluster watersheds. And they're noticing that if they extrapolate from the amount of mass they assume for different regions of space, these superclusters, then they've made this map. Oh well. I'll just show you a little movie. This is their movie. Now to me, that looks a bit like a ring. There's some confusion about what's flowing where, but certainly there's this sort of structure in the data. And they're hammering the community to look at this and take it seriously, but everyone's got their own bandwagon to push, and a lot of folks aren't interested in supercluster watersheds, extrapolated from estimates of dark mass. But there it is. And I think the note for me to finish on, sorry about going over, is that if we think of the local sheet, so Grand Universe, McCall's Council of Giants as the inner edge of that first outer space level, then this this ring, this possible contender for a ring, could well be thought of or modelled as a second outer space level, because it's there in the data, this structure. I spent a long time on this. What we've got here is that it actually fits beautifully, because the redshifts, it's the Norma group and Perseus Pisces and Pavo Indus, these major superclusters, clusters of clusters, they're all about the same distance away, 230 million light years. They're all about the same sort of redshift. Like McCall's Council of Giants, they're sort of holding formation. They're sort of sitting at that redshift distance. and with an implied motion, or well, this is an implied motion rotating around us, because we're right in the middle of Virgo supercluster. We're locked in there, so that's sitting there in the data, and we have this idea of a second outer space, or first, second, third outer space level. But here's the punchline. We can't, beyond about 100 megaparsecs, 300 million light years, we can't detect sideways motion. We can extrapolate from polarization and stuff, but there's really no hard, reliable way to detect transverse velocity. And if you think about it, this ring of superclusters, they're all around 230 million light years away. So if in fact we are halfway through the expansion phase of space respiration, then for the past 500 million years, space has been expanding. No wonder we're led to assume a Hubble flow. Because this is all, in cosmology, this is all very local stuff. For us, it's enormous, it's a long way away, but in cosmology, where you're modeling the universe, all this is considered local. So they've found this sort of Hubble flow in close, out to 300 million light years. Obvious, Occam's razor, you slice away with the data and say, let's assume that it's isotropic and homogeneous, and that it is a Hubble flow, it's the same everywhere. And that's where cosmology is currently up to, until someone else sort of throws something interesting into the mix. And that's really where I wanted to get to, because the rest is just zipping back to those 7 small teams of ancients of days stepping out from Havana. We'll call a halt. Oh, let's get to that last little bit about the 7 master spirits. I think of these little extrusions here. This is the influence of those 7 master spirits. That's the picture I have in my mind. They are impinging upon their slice of the grand universe wheel. Thank you very much.